In this video, we're going to be looking at the fundamental theorem of calculus. The idea behind the fundamental theorem of calculus is we've been looking at taking the limit of the Riemann sum from I equals 1 to n of f of x of I times our delta I, and we've been finding the area under the curve of a function using this Riemann sum. And we said this is equivalent to this definite integral. So today we're going to be looking at how do we evaluate this integral. We're going to be using the fundamental theorem of calculus to do that. So first of all, let's define the fundamental theorem of calculus. If f is a continuous function on the interval a to b, then the integral of f of x dx from a to b equals f of b. Now, capital F means we found the antiderivative and we're evaluating the antiderivative at b minus the antiderivative evaluated at a, where f is any antiderivative of f, that is a function such that f prime of x equals f of x. Now, let me give you an example to help explain the fundamental theorem of calculus. If we looked at a velocity function, let's say we have velocity and time here. We know that if we find the integral of this velocity function on this interval, we are actually finding the area under the curve. And we've discussed that if we find the area under the curve of a velocity function, that is actually finding the distance traveled. So this would represent distance traveled. What if I gave a position function related to this velocity curve? Let's say the position function looks something like this, from A to B. How would we find the distance traveled if we had a position function? This is our s of t. So to find the distance traveled, we would take our s of b minus s of a. And that would give us the total distance traveled. So we could say that s of b minus s of a also gives us the distance traveled. So we can see these two are equivalent. If we take the antiderivative of velocity, that gives us our position function. So we can see the antiderivative of velocity gives us position, and we're evaluating the position at b minus a. So that should help explain the fundamental theorem of calculus here, because we're taking the antiderivative of some function, which gives us this, just like we did down here. We're taking the antiderivative of velocity, which is the position function. That's the antiderivative. And then we're evaluating the antiderivative at S of B minus S of A. Here's an example. Evaluate the integral e to the x dx from 1 to 3. So we are going to evaluate this integral by using the fundamental theorem. And the fundamental theorem says if we have an integral e to the x dx, we are going to find the antiderivative evaluated at 3 minus the antiderivative evaluated at 1. So the antiderivative of e to the x is simply e to the x. Now I like to put this intermediate step in to organize my work. I'm going to evaluate this from 1 to 3. So now I'm going to plug in 3 to my antiderivative, so I'd have e to the third minus, I'm just following this rule right here, now I'm going to plug in 1, so e to the first power. And there is the antiderivative of e to the x dx from 1 to 3. It's e to the third minus e to the first. And that's just some number. E to the third is a number minus e to the first, another number. Find the area under the parabola x squared from 0 to 1. Again, we can use the fundamental theorem to find the area under the curve from 0 to 1. And we had set up the integral this way. That's finding the area under the curve of x squared from 0 to 1. So the antiderivative of x squared is x cubed over 3, and we're going to evaluate that from 0 to 1. So we would have 1 cubed over 3 minus 0 cubed over 3, which is 1/3. So you can see this process is much more efficient than the limit process that we've been using in the past. Evaluate 1 over x dx from 3 to 6. So I'm going to rewrite it as 1 over x dx. Now we know the antiderivative of 1 over x is the natural log of the absolute value of x, and we're going to evaluate that from 3 to 6. So we would have the natural log of 6 minus the natural log of 3 using the fundamental theorem. And if we wanted to rewrite this as the natural log of 6 divided by 3, that would be using properties of logarithms. Find the area under the cosine curve from 0 to b, where b is between 0 and pi by 2. Now this problem's a little bit different than what we've looked at in the previous three examples, but we can still solve it in the same manner. We're trying to find the area under the curve of the cosine graph. So if we want to find the area under the curve of the cosine graph, we're going to integrate the cosine. And we're going to evaluate it from 0 to b. It's not allowing me to erase that line. That's a line we don't need. Now, thinking about what's going on here, we have the cosine curve, and it's saying we want to be able to find the area under the curve from x equals 0 to some value b. And then b has to be between 0 and pi by 2. So essentially what we're going to be finding is an expression that will allow us to plug in a value between 0 and 2 pi to find the area under the cosine curve up to that point, whatever point we choose. So the antiderivative of cosine is sine. We're going to evaluate that from 0 to b. So we would get, applying the fundamental theorem, the sine of b minus the sine of 0. Now we know the sine of 0 is 0. So we get the sine of b. And again, what we're looking at is this expression right here will find the area under the curve of the cosine graph from 0 to any point b we choose. So if we wanted to know the area under the curve from 0 to pi by 4, we could find this area by plugging pi by 4 in for b. That would be the square root of 2 over 2. There's the area under the curve. If we wanted to find the area under the curve up to pi by 3, we wanted to find this area, we would plug in pi by 3 for b, and we would get the area under the curve is square root of 3 over 2. So that allows us to be a little bit flexible with finding the area, and we define b has to be between 0 and pi by 2. So this graph just gives you the graphical representation of letting b equal pi by 2, so we found the area in the curve of the cosine graph from 0 to pi by 2. Now we have to be careful when we're evaluating an integral, because this particular integral, it looks like we could just proceed as we've done in the last couple of examples. We could say we're finding the antiderivative of x to the negative 2 dx, and then we could just say the antiderivative is x to the negative 1 over negative 1 evaluated from negative 1 to 3. Now if we rewrote this, this is just negative 1 over x. We're evaluating from negative 1 to 3, and we could say we get negative 1/3 minus a negative 1 all over negative 1. And so we could say, well, we're just going to get negative 1/3 minus 1 is negative 4/3. However, this is incorrect. If we looked at this graph, we would see that on the interval negative 1 to 3, this function is undefined at x equals 0. So it's not continuous on this interval. So we have to be careful when we're working with an integral. Is the function continuous on the interval? If it is not, we can't apply the fundamental theorem. We can find if this integral, if this value exists or not, but we do that in calculus 2. But for calculus 1, we're going to say, well, this function is not continuous on the interval from negative 1 to 3, because here at x equals 0, it's undefined. So we're just going to say at this point, this does not exist. We have a second part to the fundamental theorem of calculus. Some books label it as part 1 and part 2. Now the difference is, looking at this equation here, we have g of x equals the integral of f of t dt from 0 to x. Notice this is like the problem we did with the cosine graph, where the lower limit of integration is some number, but the upper limit of integration is a variable x. So we could find the area under a curve from a to any value of x that we want to find it. So this actually creates a function. G of x is now a function because we have an input. We can input a value for x to find the area under the curve, and we have an output, the actual area under the curve. So for instance, if I have a function and I'm looking at finding the area under the curve from a to x, let's say this is a here, now if we kept track of values of x here, a distance from a, so for instance, let's say we chose this value to plug in for x. So let's just say that's x sub 1. We would have an area represented by plugging that value in. Let's say that value is, we have an area of 2. Now if we plugged in another value, say x sub 2, we'd be finding this area under the curve. And we can see that value for that x sub 2 would get larger. So let's say that is 4.2. Then I could plug in another value, let's say x sub 3, and we would get this area. So let's say that's 6.1. So we could keep plugging in values of x and getting out the corresponding values for the area. That's why we consider this a function. And if we got over here to say x sub 5 or x sub 6, we can see this would give us negative area, so we'd be subtracting off a value from our areas here, because this area would be negative. So this is called the accumulating area function sometimes, or Some books say this is just part 2 of the fundamental theorem of calculus. But this g of x now represents a function because we have an input and we have an output. Whereas the fundamental theorem of calculus that we looked at previously, the upper and lower limits were just some number, so we would get just some value that represents the area under the curve from A to B. B was not changing, as in this case the upper limit is varying. So we have an input and an output. So that's why this represents a function. So an example is in the middle of the slide. If we have g of x equals t dt. Now the reason we're saying this is t dt instead of x dx is we're letting the upper limit vary, and we're saying that's our variable x. However, this t dt is also a function of x. However, just to keep these x and t values straight, we say t dt instead of x dx, so we don't confuse the upper limit of integration with the function's value of x. Now notice what happens if we integrate t dt. We would actually get if we integrate t dt from 0 to x, the antiderivative of t is t squared over 2 evaluated from 0 to x. Notice now when we apply the fundamental theorem, it puts it back into terms of x. So we'd have x squared over 2 minus 0. So that's where we're getting x squared over 2. Now, here's something that's interesting. Notice that g prime of x equals x. So here we looked at finding the antiderivative of t dt, and we found this to be x squared over 2. What if we were to take the derivative of the results we found right here? If we took the derivative of x squared over 2, we would get 2x divided by 2, which equals x. So, if we are taking the derivative of the accumulating function, or some people call it the area so far, or the accumulating function, notice g prime is going to give us back f. Now that's just going to give us back our integrand in terms of x. So we had t dt as our integrand. Our integrand is t. When we took the derivative of g of x, we got back just x, because we went through the process of finding the antiderivative, and then we used the fundamental theorem, which gives us a function of x, x squared over 2, but then when we take the derivative of g of x, we simply get x, which is the same as our integrand, but only in terms of x. So the fundamental theorem of calculus. This is the area so far function that we just described. And notice the last line. It says this is a continuous function on the interval a to b and is differentiable on the open interval a to b, and g prime of x equals f of x. Now that's only when we're taking the derivative of g. Does it equal f of x? Find the derivative of this function. Now if we look at the results up here, it says g prime of x equals f of x. So that indicates that if we want to find g prime of x, g prime of x should just be our integrand in terms of x. So this would be the square root of 1 plus x squared. Because remember, if we take the antiderivative of this, it will give us the antiderivative in terms of x because we'd evaluate it from 0 to x. We would have this antiderivative evaluated from 0 to x. Now this puts it back into terms of x. And of course we'd have some constant of integration plus c. But when we take the derivative, now the derivative would be f prime of x. You can see that we're back into a function of x. So that's why we can just rewrite it this way here. G prime of x would equal the square root of 1 plus x squared. Now, here, remember, if we take the derivative of this f of x plus c, if this f of x happens to be a composite function, we would have to apply the chain rule. So if we had an f of g of x as this portion right here, when we take the derivative, we would have to apply the chain rule. So this would be f prime of g of x times g prime of x. So don't forget, we would have to apply the chain rule if that function happened to be a composite function. That comes about, we will get a composite function if this upper limit here is something other than x. If this was x squared or x cubed or 3x to the fifth or some other value other than just x, then this will now be a composite function, so we would have to apply the chain rule like we did right here. Now here's the case where our upper limit now is x to the fourth. So if we're looking for the derivative of this, we know the derivative would be our integrand. So we would have secant of x, but x is x to the fourth. So we'd have secant of x to the fourth times 4x cubed, because we would have to be applying the chain rule here. Because if we took the antiderivative of secant of t, we would get the antiderivative of the secant of t, but we would plug in, it would be f of x to the fourth. Now when we find the derivative of this, we would have the derivative of capital F, which was the antiderivative of secant. So the derivative would be secant of x to the fourth. But then we would have to multiply by the derivative of the inside function. So we'd have times 4x cubed.